This is section 10.2, part 2. All right, we were about to start example 5. Now we've eliminated the parameter to turn parametric equations into rectangular equations. Now we're going to find out how to find a parametric equation for a given graph. So going from rectangular to parametric. So here is a rectangular equation, y equals 1 minus x squared, and we're supposed to create parametric equations for that. And they're actually going to help us a little bit. They're going to say, let's let t be x. Well, they've already told us the first half what x is as a function of t. It's t. No big deal. That's half of it. The second half is going to be found by taking for every x in our rectangular equation, replace it with what x is equal to, t. So it'll be 1 minus t squared. That is the simplest way to rewrite. Let x or y be t and substitute into the other one with that, and you get your parametric equations. So that's like the easy answer, the one that always works. Now this one is a little bit different. They want the slope m to be our parameter, where m is dy dx, the derivative, at the point xy. Okay, so that means I need to find out what dy dx is. So looking at the equation, if y equals 1 minus x squared, dy dx is 0 minus 2x. And we're going to say that's equal to m, our parameter. So to get the parametric equation, we'll want to solve that for x. And that'll be negative 1/2 m, or m divided by negative 2, or something like that. Okay? So that's our first answer. Then substitute for each x in the other equation with what it's equal to, 1 minus negative 1/2 m squared. And so that simplifies. Of course, the x isn't changing. I'm just rewriting it so they appear together. That simplifies to be y equals 1 minus 1/4 m squared. Okay? So that's the answer for that one. Okay. Now let's graph this one and see what's going on for the second one. I think that's a little bit more interesting. So for the second one, let's look at its graph. I think that'll be enlightening. Okay, so the x and y axes. I know what 1 minus x squared looks like, so I'm going to use that information to plot a fairly decent graph of that, but I'm not going to put arrowheads because that would indicate direction of movement, and I don't want to indicate that in a false way. So, oh, wow, that was just really about bowing out a lot. Let's see if I can make it look better. Okay. So, if m is the slope, as m increases, you're going to have slopes like, I'm just going to make these up, a slope of negative 4, and then a slope of negative 1, and then a slope of 0, then a slope of 2. Not in any particular order, I'm just saying these random numbers. Those slopes are increasing. So look at our graph. Where would the tangent line have a slope that's negative? Well, it's way down here. Let's say that's got a slope of -4, just for sake of argument. Then where would it have a slope of -1? Well, it's not as steep, but still negative, right? Right there. Then 0 at the vertex. And a slope of 2, let's say that's right here, right? So the orientation is we're going this way along this curve. Okay. So that is an interesting little thing. So 6. Determine the curve traced by a point P on the circumference of a circle of radius A rolling along a straight line in a plane. Such a curve is called a cycloid. Okay, let me give you an example of how we produce the cycloid in your mind so that you get it. Say that you're in your car and there's a piece of gum on the road, and you run over that piece of gum with your tire and it sticks to your tire. So right when you touch the gum, it's on the road right there. And then as your tire, let's say this is your tire right here, make it kind of a light looking thing. If that's your tire, as your wheel rolls, at a later point in time, let's say when you're right here, it's maybe up to here. And then at a later point in time, it's up here. And then later on, it's right here. So it's moving around the tire. So let me draw a better curve, kind of connect those dots, if you will. And so this is what the graph should look like. It's going to start here. It's going to go up to the top of the tire, then down, and then be back at the ground. And then it's going to repeat, boink, and do this. And these are all supposed to be the same. It's supposed to be a periodic function, boink, etc. Okay, so that's the direction it's moving along that path. That's what we call a cycloid. And I don't want to go through the development of how they get the equations for this. I'm just going to say that the equation of a cycloid ends up being x is equal to a times theta minus sine of theta, and y is equal to a times 1 minus cosine theta. And let me define a couple of things for you so that you understand perhaps where that came from. The angle theta is, let's see if I can draw a picture. So this is where the tire is at some random point. And this is where it started. And so the angle that you've turned through to get to this point here, where the gum is now, that's theta. Okay. So theta is how far you've gone along that. And we're going to assume that the circle has a radius of A. So this radius is A. And that's where the A comes in, is the radius of the circle is A. Okay. So, like I said, you don't need to know the development of that. I don't really even want you to memorize that. I just thought it would be an interesting thing to see an application of parametric equations. This is a good application of them. Okay, so this leads us to something that we could do with that is we could find the derivatives of those equations. X prime of theta would be A times the derivative of theta with respect to theta is 1 minus the derivative of sine of theta is cosine theta. And by the way, this point right here on the curve, that point right there, is at the point 2 pi a comma 0. 2 pi a comma 0. And the next one where it touches is 4 pi a over 0. But I'm looking at those points where it touches the ground again to see what's going on there. And so if I were to put 2 pi times any integer, a is, we're going to assume, is some integer value, this will be a times 1 minus the cosine of any multiple of 2 pi is 1, and 1 minus 1 is 0. So x prime at that place would be 0. Now let's do y prime of theta is the constant a times the derivative of what's inside. The derivative of 1 is 0, minus the derivative of cosine theta is negative sine of theta, so that ends up being a sine of theta. And again, what is the derivative at any multiple of 2 pi? And that would be 0. Sine is 2 pi is 0, times a is 0. So what's happening at those points is we're having kind of a weird kind of point there that it comes to and then turns around. So parametrically, when both of those are equal to 0, then we say that the curve is not smooth. At those points. It comes to a jagged point, okay, at that point. So that little point at the bottom of that curve is a point where it's not smooth. Otherwise, the curve is smooth, because if you look at the definition of a smooth curve, if you have parametrically defined curve, x equals f of t and y equals g of t on an interval I, it's called smooth when f prime and g prime are continuous on the interval and not simultaneously 0. And of course, these are simultaneously 0 at multiples of 2 pi. So that means that it's not smooth at any of those points. The curve C is called piecewise smooth when it is smooth on each subinterval of some partition of I. So from 0 to 2 pi a, it's smooth, not at 0, not at 2 pi a, but everywhere in between it's smooth. Okay, so that'd be kind of an interesting thing. Okay, so now we're going to investigate a couple of problems that are famous in the calculus world, and it's related to the cycloid. The first problem, called the Tata Crone problem, began with Galileo's discovery that the time required to complete a full swing of a pendulum is approximately the same whether it makes a large movement at high speed or a small movement at lower speed. There's a little picture there, figure 10.26, that you can look at. Galileo realized that he couldn't use this principle to construct a clock. However, he realized that he could use this principle to construct a clock. However, he was not able to conquer the mechanics of actual construction. This other gentleman, Christian Heinz, I think is how you say his name, was the first to design and construct a working model. He realized that a pendulum does not take exactly the same time to complete swings of varying lengths. But in studying the problem, he discovered that a ball rolling back and forth on an inverted cycloid does complete each cycle in exactly the same time. So if you invert the cycloid, and we only want to look at one of them, and you have a ball rolling here along this path, it will, as he found, complete each cycle in exactly the same time. Okay, the second problem, which is posed by Bernoulli in 1696, is called the Brachistochrone problem. In Greek, brachis means short and chronos means time. The problem was to determine the path down which a particle will slide from point A to point B in the shortest time. So you could have like an inclined plane from point A to point B. And you may think, well, that's the shortest distance between two lines. The ball should travel from A to B in the shortest time if it is a linear thing. Well, actually that's not the case. As it turns out, an inverted cycloid, if this is A and this is B, you'll travel fastest along that curve, along that path, the inverted cycloid path. That's the fastest you can get there. Interesting, huh? And the amazing part of this solution to the Breakfasty problem is that a particle starting at rest at any point on the cycloid between A and B, so if it actually started, let's say, right here instead of up there at A, it started, say, here and went to B, the particle starting at rest at any point C of the cycloid between A and B will take exactly the same time to reach B. So it doesn't matter where you started. It's going to take the same time to get to B no matter where it started between A and B. And I think that's really cool. All right, so that ends that lesson. I will see you in class.